In this video I'll tell you about grids and their special role for simulating flow in porous rock formations. I will assume that you are familiar with the concept of a grid and that you also know how grids can be used to formulate spatial discretizations of partial differential equations. In reservoir simulation we are interested in flow behavior inside a bounded domain, like the L-shaped red figure you can see. Single-phase flow in homogeneous isotropic rock can be described by an elliptic Poisson type equation. To discretize this equation, we introduce a partition of the domain. Then we use a standard finite difference or a finite volume method to derive a set of discrete equations for the unknown pressure associated with each cell. In most university courses, the grid you encounter will either be regular Cartesian grids, like the one shown in the figure, or consist of triangles or tetrahedrons that adapt to external or to internal boundaries. The main purpose of such grids is to formulate the spatial discretization. And the number of grid cells is typically chosen to ensure that this discretization has a certain accuracy. Grid models used to represent real reservoirs are different, and they are more complex than the L-shaped problem shown in the beginning of the video. The primary purpose of a geological model is to provide a 3D geological map of porous rock formations. We therefore choose cells so that they represent regions in which the petrophysical properties show small variation. This means that real grids are irregular and have complex cell connections. The number of cells can obviously be adjusted to change the accuracy of the discretized flow model, but doing so is a bit more involved, since we then also need to change the petrophysical parameters inside each cell. Let us look at the Gullfaks field from the Norwegian North Sea as an example of a so-called stratigraphic grid. These grids are made to represent the stratigraphy and the structural architecture of the reservoir. Think of this Cartesian box as a layer of sediments that have been deposited throughout history, where red color represents older sediments and blue color newer sediments. Sediments are not deposited evenly, and certain regions will be more eroded over time. This means that we should eliminate several of the grid cells in this model. Given this layering, we can populate each cell with petrophysical properties that are representative of the distribution of deposited particles. As deposits are buried, geological processes will introduce faults and folding, fractures, and so on. In this figure we see a cross-section of the Gullfaks model. The upper plot shows a grid in index space, which gives a geological layering. The second plot shows actual cells that are present in the model, and the third plot shows the vertical permeability in each of these cells. The last plot shows the cells in physical space, and here we can notice how the faults introduce connections between cells that are not topological neighbors, hence connecting rock volumes that have been deposited at different times. In the other videos in this Jolt, I will tell you more about how you can use MRST to represent and generate grids like you have seen in this video, starting from simple Cartesian grids and going on to complex stratigraphic grids.